My talk is about the spatial variability of urban sinks and microclimate in the city of Helsinki. So I will start by introducing why we are interested on the biogenic CO2 exchange in urban areas. My PhD has been about simulating the biogenic CO2 exchange, so I'm going to describe the model that we are using and then show how the results spatially vary as a function of land use. So there are two main reasons that we are interested. The first one is that cities are striving toward carbon neutrality and they want to offset part of their emissions by their own vegetation. And at least the city of Helsinki is already doing this based on these biomass growth equations that are based on forest measurements. So there's a lot of improvement that could be done. The second one is that biogenic CO2 exchange in urban areas is seen as an uncertainty in urban measurements because most of the people are interested on the anthropogenic emissions. So to get those, we really need to estimate what is the biogenic component. And as Leena showed, we need measurements for that. However, they alone are not enough to address the high spatial variability in urban microclimates and vegetation coverage that are affecting the CO2 uptake if we want to estimate the city scale uptake. Therefore, we need to develop modeling tools that can take this into account. So the aim of my study was to estimate the spatial variability of local air temperature, so the local humidity air temperature, and the biogenic CO2 exchange in the city of Helsinki, Finland, and then assess how vegetation of different urban habitats would contribute to the cooling and carbon sequestration, and we did this by grouping the results based on the local climate zones. So Zeus model was already mentioned today by Tom. So it's an urban land surface model originally created by Supriman, but in 2019, together with Leena, we added the CO2 components to the model. The model is forced with hourly meteorological variables, and it's given detailed surface information. So here are the 7 surface types given to Zeus. So, yeah. And what interested me in this model is also that it simulates the local conditions. So it simulates the air temperature within the roughness sublayer so that we get the humid air temperature. And it depends mostly on how much there's vegetated areas and built-up areas and how these affect the sensible heat flux. Then it also simulates the soil moisture conditions because it takes into account how much there's irrigation, precipitation, and how much there's runoff from the grids, and how much the trees are transpiring. And why I was interested on this, because in our model we take these into account. So we estimate the maximum potential for photosynthesis from measurements, and then in the model we scale this value with seasonally varying leaf area index. That is also simulated by this Zeus model, and then this potential value depends on this Jarvis type of functions: solar radiation, air temperature, specific humidity deficit, and soil moisture deficit. And these relations were already included in the model as the stomatal conductance depended on these functions, and that was used in the modified Bellman-Montaigne evapotranspiration equation. And then the vegetation and soil respiration builds only on the local air temperature in this model, and this is something that we would like to develop further to include the soil moisture at some point. And we have parameterized the model based on either eddy covariance or chamber measurements both like soil sample measurements and like leaf level sample measurements. And we have evaluated it against eddy governance measurements in Helsinki and Beijing, and also against street tree level measurements. And if you are interested on any of that, go read these papers. They are part of my PhD work. Then, to the actual model run done in this study. We have further parameterized the model and classified these. There were the evergreen and deciduous trees and grass fractions, and we have further divided them into urban forest, parks, street trees, lawns, or other mixed low vegetation based on the measurements that Leena has showed, but also used measurements from Harvard Forest and Yhtälä Forest in Finland, because we didn't have any urban forest eddy governance measurements available. Here you can see the city of Helsinki divided into 250 times 250 square meter grids, and we did two different study cases. So one was for the present climate, so we simulated years 2015 to 2019 with how the resolution and the forcing data came from this 2.5 kilometer resolution reanalysis dataset that is shown on these right-hand side figures. And they also had this post-processed dataset that had a 1 kilometer resolution. We also did the future climate projection under the RCP 8.5 scenario, so the extreme scenario for 2050s, and this was done by Saran et al. Already in 2020. But here we only took into account the effects of the meteorology, and there was no changes in the land use. So the results. So first showing the annual mean 2 meter air temperature values, and here you can see the local climate zones found in Helsinki. So there were 8 classes found. So I used these European level city maps that were readily available. In both of these figures you can see that the red area, so the city center, is the warmest. And compared to the forested areas, so the green areas in the LCC map, the highest difference was 5 degrees in the annual mean temperatures. However, when we group these to local climate zones, the difference between all of these urban neighborhoods and the vegetated classes was only 1 degree. And when we did the future climate run, the expected increase for the whole area was 1.3 degrees of Celsius. However, the compact mid-rise class was increased a little bit more than what the dense trees class increased. Then, how the spatial variability of the CO2 exchange looks like compared to the local climate zones. So now the city center is really close to 0 because the amount of vegetation there is quite low. The blue color indicates higher sinks, and red one the sources of CO2. The forested areas are really highlighted in here, but you can also see that the orange areas that are the suburbs of Helsinki have still quite significant sinks. And grouping these to the base of the local climate zones, we can see that yes, the dense trees were on average 0.3 kilograms of carbon per square meter, and as they while they covered only a quarter of Helsinki, aerially, they contributed to 44% of the city's net uptake. And while the vegetation classes of vegetation within the urban neighborhoods were weaker sinks because they spanned to so large area, they can contribute to 47% the city's net uptake. And when we took into account how the air temperature and the soil moisture conditions would affect the CO2 exchange in 2050s with the RCP 8.5 scenario, we found out that there was an increase by 11% in the CO2 uptake. There's two reasons why it's like this much. The air temperatures lengthened the growing season, which increased the sink, but during summer months, even though the amount of precipitation annually was increased, the distribution was a little bit different. So there were long periods during summer when the soil dried out in forest areas, which decreased the sink. Of course, when there's irrigation, that meant that the effect wasn't seen there. So to conclude, we estimated the spatial variability of these two variables in the city of Helsinki with this urban land surface model suits, and we estimated how these different urban habitats would contribute to cooling and carbon sequestration, and an estimated 11% increase in 2050s was found with this RCP 8.5 scenario. Thank you.
Thank you very much for the very nice talk. Do we have questions from the audience?
Yeah, thank you very much. My name is Benjamin from Meteorological College. Yeah, from literature, I used to know that seals underestimate the incoming solar radiation because it couldn't simulate the cloud cover correctly because it depends on some environmental variables, relative humidity and air temperature. So I want to know if that would affect the result of these simulations, I mean the underestimations, the bias in the incoming solar radiations. Did you understand the question?
I'm not sure, so we are taking it into account. So, sorry, what was the question? Can you?
Yeah, the question is that seals
Yeah.
have the potential of underestimating the incoming solar radiation.
It's given as an input to the model.
It's given as an input.
Yes, from the reanalysis product.
Thank you for the presentation. The observation study shown by Leena showed that lawns were a carbon sink, but the modeling shows lawns as a source. Can you comment on that?
Yes, I think there was like even Leena showed that the new lawns were a source of CO2. So there's a little bit of difference, like depending on the year also, because they can be a source of it. So it's really like highly variable. And if there's enough irrigation, it's usually a sink. But these areas where like fields mostly or like mixed vegetation, they have a much larger like respiration than this lawn had.
Thank you.
Thank you so much. I think we're good to do